Hello guys, I am Amin. In this video I want to show you how to simulate the complete cycle of internal combustion engines. So join me to learn a very easy way to do this. You should look at the three parts of the engine package simulation that I made earlier, because I don't want this video to be long with a repetitive task, and it's only for complete cycle simulation. If you have watched the previous videos, you will remember this domain, which has three boundaries with piston, liner, and cylinder head. I also showed you how to completely set up this closed cycle diesel engine. For the full cycle, I want to do with just some simple changes to this geometry. For that, we need some extra domains. Here I have already prepared the necessary domains and named their boundaries. In the intake domain, we need an inlet. We need the intake port wall. And the valves contain with three boundaries, named with valve top, valve angle, and valve bottom. And this remaining part is a piece of cylinder head. Here I must mention an important point, that the cylinder head is directly connected to the wall of the ports, and the space between the valves and the cylinder head is empty, while the valves are connected to port walls from above. This is because we are working with surfaces and we want to avoid non-manifold problems. Here again we have inflow or inlet, intake port, intake valve top, intake valve angle, and intake valve bottom. Similarly, we have for exhaust domain with outflow or outlet, exhaust port, exhaust valve top, exhaust valve angle, and exhaust valve bottom. After you specify the names of these boundaries, you just need to export this STL. After that, simply go to the closed cycle project and drag and drop your STL file into the domain. How easy was that? Now you can see all of my boundaries from STL file imported to my closed cycle project. It seems it fit very well on my geometry, but I need to do some changes. Before that, let's close this unnecessary project here. Firstly, we need to delete our old cylinder head domain. To do that, go to Geometry, Repair, and Delete tool. Choose selected boundaries from input method and select head and click Apply. Let me disable the injectors for now. Here, because of the test, I just want to remove a pair of valves. For that, let's go to the View options and just show the intake and exhaust port domains. For selecting them, I use this square selecting tool from the top, and with the delete option, I completely remove those unnecessary ports. Now we need to move this port to the center of our cylinder. For that, we translate by selecting direct direction vector and choosing the ports boundaries. And I give it an amount of 0.01 meter. Here we need to change the direction from z-axis to x-axis. and I roughly move them to the center of the cylinder. Here for filling the space between port and liner, for creating a head boundary, we need to go to the repair and select patch tab and choose patch around the holes. For inner loop, we need to select the part we mentioned earlier, which is a part of cylinder head. And for the outer loop, we need to select the arc around the liner. Now with enabling the surface mesh, you can see the ports and the closed cycle domain are connected together. Here we need to combine our new surface with our head boundary. I noticed that the ports are small compared to the cylinder domain, so I start from the beginning by pressing Ctrl Z. I want to scale the ports from the transform and scale option. And again from the repair and patch tool, I do the same work for filling the space between ports and cylinder liner. After that, again I combine the cylinder head boundary. Now our geometry is ready. Let's jump to the case setup. First of all, you may need to fix reference surfaces from the engine properties section. Here make sure you select the correct boundary IDs for each references. Now with compression ratio tool, select the boundaries around the combustion chamber, and from below you need to select the piston boundary. We just need a small displacement to get our compression ratio. Here our engine properties are the same, also materials are the same, and in the simulation parameters we just need to change our simulation time from IVC to EVO to 0 to 720 crank angle degrees. Here we can use a tabular max CFL number to reduce our computational time. For that I give a 5 before the IVC and 1 for IVC to EVO and 5 after EVO. I named it CFL and make sure that give it a .in file format, end of it. Now other inputs of simulation parameters are the same. Also we don't need to change any physical models in here, like spray or combustion model. Here, for converting our closed cycle simulation to open cycle simulation, we just need to change our boundary and initial conditions. Also we need to change our grid control. For the initial boundary conditions, I want to import my previously prepared setup. Here we have the cylinder domain. Intake domain and exhaust domain. This is my initial parameters for my cylinder domain. Also, these parameters are close to my exhaust port domain. And this is my intake port inputs. After that, we need to set up our boundary conditions. Let me first import my prepared boundary conditions. Similarly, we have piston, cylinder liner, cylinder head. Now we need to specify valve type for intake port and also translating valve type for intake valve top. For these boundaries, we need to use valve leaf profile. These profiles shows the valve movement with the crank angle. Here in Excel, I prepared my own intake valve lift and exhaust valve lift. I just copied the columns from the Excel and paste it to the software. Give it a name with the .in file type. This intake lift file will be used in intake valve top, intake valve angle, and also intake valve bottom. I use total pressure of 2 bars for my inflow boundary and give it a temperature. Also, if you are using the ECFM3Z combustion model, you need to input a unmixed species. And similarly for the exhaust domain, we need to use a exhaust valve lift profile for each of the exhaust valve top, exhaust valve angle, and exhaust valve bottom. Also input the conditions of the outflow with the pressure and temperature. Also here we don't need to use unmixed species at the outlet because our species are mixed after the combustion. After that, we need to specify regions for each boundaries. We have the piston, cylinder liner, and cylinder head for the cylinder region. Also, we need to specify intake valve bottom plus exhaust valve bottom with the cylinder region. In here, we need to add events option in our case setup. This setting controls the transfer or entry and exit of fluid from one domain to another. That is, it does not need to be completely closed between the area of ports and the combustion chamber. We just need 2 events for the intake valve and exhaust valve. Just specify the region A to cylinder and region B to intake and exhaust ports. By selecting the event type to valve, it will automatically get the start and end of the event from the valve profiles. Here for the test, I want to increase our base girth size to 6 mm. Also, let me import my AMR file. Here we just need 2 groups of AMR. One for cylinder and second for our intake port. Our cylinder AMR is similar to our closed cycle simulation that we specified before. But for the intake domain, we need a small amount of embedding for the velocity. For the fixed embedding, we have the same embedding near the injector. But we need a finer mesh near the intake valve and exhaust valve angle because of avoiding intersection problems. You will need larger scales of embedding. If you don't know what level of scale you want in near this boundary, don't worry, the CONVERGE will suggest a scale level based on your base girth. For the better understanding, I want to show the intake valve angle in our domain. This is all of our valve surface. This green boundary between the top and bottom of the valve surface is our intake or exhaust valve angle. Sometimes they say valve seat in other simulation softwares like ANSYS Fluent and also the AVL Fire. In the output settings, select whatever you need, such as the heat transfer of the valves. Also give the time interval for writing 3D outputs. I give it every 3 crank angle. Also your time interval for writing restart files. I give it 15, and maximum number of restart files you want to save. Lastly, select your desired post variables and results. Now your project is ready. You can run Converge. And now I have to say good luck and wait a week for it to finish.
2,000 years later.
Oh my god, finally after 15 exhausting hours, the calculations were completed. This was just a test and we need much more time for more accurate calculations. These calculations are not efficient with a laptop and a workstation computer is definitely needed. Now let's import our 3D result to the tech plot. Insert a slice at the middle of the domain. Also make the boundaries transparent. Let's change our variable to the velocity. Give it an approximate levels. Increase the number of levels. And now we can see the velocity behavior in our engine. Also, you can extract a lot of result from your calculation. Thank you guys for being with me in this video. I wish you success and have a nice day.